Hello everyone, my name is Vipin Mishra. I am the lead mentor at IMS Gate Academy and I welcome you all in this Gate Score Booster series of IMS Gate Academy. I hope that you all are preparing very well for the Gate exam, and right now you are revising and giving so many tests, and in the meanwhile you are enjoying our Gate Score Booster series as well, right? So many subjects we have already taken in this series, and today I am going to start today I am going to take very important and scoring subject for electrical engineering students, and that is none other than the electrical machines, right? Electrical machines. Okay, so today I am going to take a session on electrical machine. Tomorrow I will take a session on power electronics, the core subjects, right? So before actually starting, let me tell you a very exciting news. This is the time where you might be revising all the subjects and you will be attempting as many tests as required, right? So for that, IMS Gate Academy is offering you test series plus program, and we are giving you this program at 20% discount right now, right? So in this program we will give you 130 plus online test along with the GQB booklet and so many other features. So 130 online test, right? If you will attempt that many number of tests, surely you are going to boost your score, right? So do join this program. Now let's get started with the first topic, which is transformer. So if I talk about the transformers, their weightage is around 2 to 3 marks. Okay, this chapter may give you around 1 or 2 questions. So the weightage may be around 2 to 3 marks. Okay, the important topics are losses and efficiency, the hysteresis loss, eddy current loss, calculation of efficiency, equivalent circuit and calculation of voltage regulation, right? Circuit referred to primary side, secondary side, auto transformer KVA calculation questions, then 3-phase transformer calculation questions of 3-phase transformer, right? So these are the important topics. Now let us start with the very first question for the day, and this is from the losses. Okay, so this is the first question. What is given? Single phase 400 volt 50 hertz transformer has an iron loss of 5200 watt, right? So what are the iron losses given? So the iron losses are 5200 when the voltage is 400 volt and the frequency is 50 hertz at rated condition. When operated at 200 volt 25 hertz, the iron losses becomes 2200. So iron losses, they are 2200 when it is operated on 200 volt and 25 hertz. When operated at 416 volt and 52 hertz, then what is going to be the ratio of hysteresis losses divided by eddy current losses? So you have to calculate the ratio of hysteresis to eddy current losses when it is operated at 416 volt and 52 hertz. So at this frequency, what is the ratio of these two? This is what you have to calculate, right? This topic in transformer, calculation of hysteresis loss, eddy current loss, is a very important topic. Many times we have seen gate question from this topic. Almost all gate paper consist one particular question from this topic. So this is very important, and this is the reason why I have selected this question, right? So how we are going to solve this question? Just see. So we know that hysteresis losses are proportional to frequency, or we can write that hysteresis losses are some constant A times F. Eddy current losses are proportional to frequency square, or we can write that eddy current losses are B times F square, where B is a constant. Total iron losses are the combination of hysteresis plus eddy current losses, or we can write AF plus BF square, or it may be written as PI over F. This is equals to A plus BF, correct? Now as per the given conditions, what are the iron losses for the first case? When the frequency is 50 hertz, the iron losses are 5200. This is equals to A plus B into 50, okay? And when we have iron losses as 2200, at that time the frequency is 25 hertz. This is equals to A plus B 25. Now we have equation number 1, we have equation number 2. So you have to solve these two equations, right? This is the process. Now you will be solving these two equations. So when you will solve these two equations, the values that I am having is the A is coming, the B is coming, when you will solve, the B is coming 0.4, sorry, the B is coming 0.8 and the A value is 62, correct. B is 0.8 and the A value is 62, right. You may verify this answer. Right. Now after that we have to calculate the hysteresis loss to the eddy current loss ratio. So hysteresis losses, they are A into F, eddy current losses, they are BF square. So we will get A over BF. Now A value is 62, B value is 0.8 and the frequency at which we have to calculate is given 52. So once you will solve it, you will get a ratio of 1.49, right. So all the calculation I have done, right, to save time and to do as many questions as possible, because I have a lot of questions to discuss. What you can do, you can re-verify these answers, right. So just see, this is how you have to deal with questions like this. What you have to remember is, you have to remember this analysis, okay. You have to remember this analysis. Through this analysis with the given value, you can calculate anything related to hysteresis and eddy current losses. So I hope that this question is clear. How many of you are getting the same answer? How many of you are getting the same answer? Will you please reply? How many of you are getting 1.49 as the ratio of hysteresis to eddy current losses? Okay, so this is how we have to deal with a question like this. Now after that, just see the second question. For a single phase 2 winding transformer, the supply frequency and the voltage are both increased by 20%. Sonali is getting same answer. Very good, Sonali. So for a single phase 2 winding transformer, the supply frequency and voltage both are increased by 20%. So the new voltage is 20% increased as compared to the old voltage, and the new frequency is also 20% increased as compared to the last frequency that we have. So this is what is given to us. The percentage changes in the hysteresis losses and eddy current losses respectively. So you have to comment that which option is correct regarding the changes that will occur with the given condition in the hysteresis losses and the eddy current losses. Very good. So Sonali and Bindu, they are getting same answer. Very good. Okay. Now can you just solve this question? If the frequency and voltages are changed, then what is going to be the changes in the hysteresis losses and eddy current losses? You have to apply the same formula that we have discussed in the last case, right? That we have discussed in the last case, and I am giving you some time to solve this question. Okay. So you have 2 minutes to solve this question. Very good, Bhavani. Frequency is changed, right? Then what are the changes in hysteresis and eddy current losses that you have to calculate? Tell me the correct answer. Meda is saying B. Very good. Lightning fast speed. You only have taken 15 seconds, I think, right? So Meda is saying that B is the correct answer. What about others? Are you also getting B? Hysteresis losses and eddy current losses means the losses and efficiency is one such very important topic. Okay, it is a very, very important topic from the transformer. So Sonali is getting answer as A. means 20% decrease and 44% increase. Okay. Bindu is also getting B. Okay. So I think we will go with B, right? Let's see whether B will come or not. So guys, we know that hysteresis losses, okay, hysteresis losses are proportional to frequency. So from here, if we will calculate PH2 over PH1, that will be F2 over F1. What is F2? F2 is 1.2 F1 upon F1. So what we will get? We will get 1.2. So the new hysteresis losses will be 1.2 times the old hysteresis losses, or we can say 20% increase, right? Similarly, if I talk about the eddy current losses, so the eddy current losses are proportional to frequency square. So eddy current losses ratio will be something like this, okay. Then if I'll put the values 1.2 F1 over F1 is square, then what I am going to get is 1.44. So I am getting new eddy current losses are equal to 1.44 times the old eddy current losses, or we can say there is 44% increase. That means option number B is the correct answer, which all of you have obtained. Very good, right? Sonali, I think you got the right answer, but you click the wrong option, right? Very good. Okay, so this is an important topic from where we can expect a gate question. Every gate paper, if you will pick, every gate paper was having question from this topic. Okay, that's why I also took 2 questions, okay, which will give you a flavor of hysteresis and eddy current losses. Now after this question, now just see this one, okay. So a single phase transformer has no load losses of 94 watt, no load losses of 94 watt. No load losses means the iron losses, and they are given as 94 watts as obtained from the open circuit test, right? When a short circuit test is performed on it with 80% of the rated current, 80% of the rated current flowing in the low voltage and high voltage winding, the measured losses are 72 watts. So losses are we are getting during the short circuit. So the copper losses, these are the copper losses which are 72 watts, okay, but at 80% of the current flowing, okay. So at 80% rating, right? So we define something called as load factor. So the load factor is 80%, or we can say 0.8. Then what we have to calculate? The transformer has maximum efficiency when operated at what load factor we have to calculate, okay. We have to calculate that at maximum efficiency, we will get maximum efficiency at what condition, okay. So they have written 50% of the rated current, they have written 8% of the rated current, or 91.4%, or 89.8% of the rated current. I hope you understood the question, correct. So what will be the percentage? So I hope that you know this formula, okay, that current during maximum efficiency is equals to current full load under root Pi over PCFL, okay. What is Pi? Iron losses. PCFL, full load copper losses. Sonali is getting answer C. Sonali, very good, okay. So we have to calculate this. So we need PCFL, okay, we need PCFL for that. So you know that full load copper losses, they are copper losses at any other load divided by the load factor, correct. So we have been given that PC is 72 and the load factor is 0.8 square, right? Everybody is getting C answer, very good, correct. So we will get 112.5. These are the full load copper losses. Now again applying the same formula, So current at maximum efficiency will be the full load current under root, what are the iron losses? 94 divided by the full load copper losses 112.5. So when you will be solving this, I hope that you are getting 0.914, right? 0.914 times I2 FL, or we can write 91.4%. Got it? So the transformer has maximum efficiency when it is operated at 91.4% of the rated current, that is the full load current. Correct? So I hope that you have done exactly in the same way, and wow, everybody is getting C as a correct answer. Very good. Very good. That shows that you have a very good touch of electrical machines, right? And the faculty who has covered electrical machines with you have covered it nicely, right? Exactly. Very good. Very good. So I hope that everybody has cleared this, solved this question. Now next question, question number 4. A 300 kVA transformer has 95% efficiency at full load, 0.8 power factor lagging, and it is having 96% efficiency at half load unity power factor. Then what is the maximum efficiency in percentage at unity power factor load? Correct. What is going to be the maximum efficiency in percentage at unity power factor load? So we have been given the two efficiencies at two different power factor and at two different loading. Then what is going to be the maximum efficiency at unity power factor load is what we have to calculate here. Okay. So I hope that you know this formula, that efficiency is M, which is the load factor, into rated kVA and the power factor divided by M times the rated kVA cos phi 2 plus iron losses plus this M square and full load copper losses, right? Where what is this M? This M is basically given load, or you can call it load factor. Okay, no need to define it separately, you can call it the load factor, right? Actual load upon the given load, it is the ratio of actual load to the given load. So this is the formula, okay, where M I will write the load factor. So in first case the load factor is basically what? 1, and in the second case it is half. Okay, so in case number 1, if you will apply this formula, then what you are going to get? So in case number 1, we have been given the value of M to be 1 because it is full load, right? And the power factor given is how much? 0.8 lagging, right? So apply the formula, and what is the efficiency? Efficiency is 95%, so 0.95 and it will be 1. Rated kVA are 300, okay, and the power factor is 0.8 divided by the same data plus iron losses, and 1 square will be 1, or we can write copper losses. So this is one equation. If you will solve this equation, you will get an equation in terms of iron losses and copper losses, and that equation is Pi plus PCFL, that you will get Pi plus PCFL, that you will get around 12.63. Let me call this equation number 1. Okay. Now under the case 2, at case 2 the load factor is given half, okay, M is 1 by 2, and the power factor is given 1, and the efficiency is given 96% or 0.96. So again apply the same formula. 0.96 is equals to half 300 into 10 to the power 3 into 0.8 divided by half 300 into 10 to the power 3, the power factor is unity. Let me write unity here, right? And iron losses plus 1 by 4 of PCFL, correct? Now just see, in this equation again the unknowns are iron losses and copper losses, right? So when you will solve this equation, what you will get? You will get 0.96 Pi plus 0.25 PCFL. This might be coming equal to 6.25. This is what I have calculated. You can re-verify this, okay? So after applying these conditions and the formula, you will be getting two equations, right? You might be getting these two equations. Now if you will solve these equations, equation 1 and 2, then you will be getting iron losses and copper losses as follow. So iron losses that I am getting is 4.18 kilowatt, and the copper losses, full load copper losses are 8.51 kilowatt, okay? So by applying the given condition, first of all you will calculate the iron losses and the copper losses, right? Now, so we have calculated this data. Now what we have to calculate, what is the maximum efficiency in percentage at unity power factor load, okay? So what is going to be the new load factor now? We have to calculate M first of all, and M will be Pi over PCFL, okay, for maximum efficiency, right? So it will be, what is Pi? It is 4.18, and what is PCFL? It is 8.51, okay? So when you will solve it, you will get the value of M, and that will be 0.7. Correct, that will be 0.7. Now if I apply the formula of maximum efficiency, okay, so it will be M into rated kVA into cos phi 2, right, divided by M into rated kVA cos phi 2, and at maximum efficiency iron losses are equals to copper losses, so I can write 2 Pi. Got it? Now just write all the values. So what is M? 0.7. What is rated kVA? 300 into 10 to the power 3, okay? Power factor at which we have to calculate is 1. Repeat the same data. Plus 2 times the iron losses that we have are 4.18, okay? So when you will solve this, you will get 96.2% as the efficiency, maximum efficiency, right? After solving it, you will get 0.962 or 96.2%, right? So option number C will be the right option, right? Option number C is the correct answer. So how many of you are getting C as right answer for this question? Have you calculated? Are you getting C? 96.2%, right? It's a very good question. Two efficiencies at two different power factor and load rating are given to us. Then we have to calculate that what is going to be the maximum efficiency at unity power factor. Got it, guys? Are you getting the same answer? Very good, very good. So I hope that this question is also clear, right? Very good. You may expect exactly the same question in the exam as well, okay? They have not asked question related to efficiency for a long time. So this time you may expect a question from this topic. Now have a look over this question. A single phase 50 kVA 250 volt 500 volt 2 winding transformer has an efficiency of 95%. So when we have 2 winding transformer, okay, so what is the efficiency of 2 winding transformer? The efficiency of 2 winding transformer is 95% at unity power factor, right? it is reconfigured as a 500 volt 750 volt auto transformer. Its efficiency at its new rated load at unity power factor will be what? Okay, you know, when we are reconstructing or reconfiguring a two winding transformer as auto transformer, the losses remains same. Okay, so what you can do with the given data, first of all you can apply the efficiency formula and you can get the losses, right? So neta, which is m into, we can write kVA as S2, m S2 cos phi 2 upon m S2 cos phi 2, and let me write losses, right? Iron losses plus m square copper losses. I am using the word losses, correct? Now we have to calculate this at full load. So m value will be 1, efficiency is 0.95, okay, and rated kVA are 50 kVA, right? And cos phi 2 is given 1. Same we have to write in the denominator plus losses. So you can see only the unknown value here is the losses. So we will calculate losses, and once we will calculate losses, losses are coming 2.63 kilowatt, right? 2.63 kilowatt are the losses. So when we are configuring two winding transformer as an auto transformer, the losses are going to remain the same, they will not change. Okay, so we have calculated the losses. This is a very important factor. I just want you to have a look over this topic. That's why I have taken this question, correct? So we have calculated the losses. Losses will remain same in both the cases. Now when it comes to auto transformer, right? So how we have configured auto transformer as 500 volt 750 volt. So just see, if suppose this is the auto transformer, okay, so auto transformer is 500 volt at its primary side and 750 volt on its secondary side, correct? So this is going to be the high voltage and this is going to be the low voltage. So if I calculate the auto transformation ratio AA, that will be VH over VL or 750 over 500. So how much we will get? Approx 1.5. Got it? Now then you know that we, in order to apply the efficiency formula, we need the kVA. So we have to calculate the auto transformer kVA. So S auto, we have a formula that it is AA over AA minus 1 S 2 winding, right? This is a very important formula. So many times they have asked question only related to this formula. We are doing so many things in this questions, correct? So what is A? 1.5 over 1.5 minus 1 S2 winding is given 50 kVA, correct? So when you will solve it, you will get 150 kVA, right? 150 kVA. Now when you will calculate the efficiency, so again what we will be doing, rated load and unity power factor is given. So m value will be 1 and S value will be 150 kVA of the auto transformer. Okay, so efficiency of auto transformer this will be, and the power factor is 1. Same data we have to repeat in the denominator, correct, plus the losses that we need is 2.63 kilowatt into 100. When you will do that, the efficiency that you will be getting is 98.27%. 98.27%. Meda is getting 98.27, exactly the same answer. Very good, right? So through this question I just want to make you comfortable in two topics, okay? That when it comes to auto transformer and the two winding transformer, transformation ratio, it is always on the high voltage side, voltage to the low voltage side, and then this formula how to calculate the kVA of auto transformer. You know, so many times they have only asked to calculate this. We have done two things here. Okay. So one question is giving you three concepts, right? That is why I have selected this question. So if you will be able to practice these concepts and question, they may ask for everything or they may ask for just one concept and you will be able to answer, right? So I hope that it is clear. Everybody is getting the same answer. Very good. Very good, Bindu. So I hope that it is clear. Nobody has a problem. Moving towards the next question. See this one. 3-phase 1000 kVA 3 kV to root 3 kV delta to star 50 hertz transformer has primary, that is high voltage side resistance per phase 0.20 ohm, okay, and the secondary or the low voltage side resistance is 0.011 ohm. Iron loss of the transformer is 10 kilowatt. The full load percentage efficiency of the transformer operated at unity power factor will be what? Okay. So when it comes to 3-phase transformer, okay, you don't have to do anything. Exactly what we are habituated of doing in single phase transformer, we will do the same thing once we will get the data. What is the data? We need to have the kVA rating, we need to have the power factor, we need to have the losses value, right? And what is the 3-phase contribution? The 3-phase contribution is you have to see the connection and you have to calculate the currents accordingly, whether it is delta or star. We know that in delta, line and phase are two different current. In star, line and phase are same current. In delta, line and phase voltages are same thing. In star, line and phase voltages are two different things. Okay. If you know all those things, you don't have to get a fear of these 3-phase questions. Okay. They will be very easily solved. Okay. So just see what we have. So we have been given the type of connection is delta to star, right? Delta is the primary side, star is the secondary side. The voltage here is 3 kV, the voltage here is root 3 kV, correct? And their power ratings are 1000 kVA. Okay. So in a transformer, the kVA on the primary and the kVA on the secondary are same, we know that, right? This side the resistance is how much? 0.02 ohms. What is the resistance on this side? It is 0.011, and we have been given the iron losses which are 10 kilowatt. So we don't have the value of copper losses, right? Copper losses are not given, and we have to calculate that what is going to be the efficiency at power factor of unity. Got it? So efficiency we can calculate easily. kVA rating is given to us, load rating is given to us. We need to have the copper losses. Once they will be known to us, we can easily calculate the efficiency. So we will try to get this data, right? So how to calculate copper losses, right? Copper losses will be, because it is 3-phase transformer, so 3 I1 square R plus 3 I2 square R, where I1 is the primary current, I2 is the secondary current. Here we will write R1, here we will write R2. Got it? So we need to get these currents. Do we have these current given to us? No, we have to calculate them. So just see for I1, okay, how do we calculate I1? So for I1, that side is delta connected, right? Now on that side, if you will calculate line current, it will be S over root 3 VL. Got it? What is S? It is 1000 kVA upon root 3 into what is VL? It is given 3 kV. Correct? So when you will calculate the current, the answer that I am having for the current is, it will be 192.45. 192.45 ampere. And what we have calculated? We have calculated line current. In the delta side, line current and the phase current are two different values. So primary current or the delta side phase current, okay, it will be different from the line current. So what will be delta side phase current? Line current divided by root 3, right? So the line current that we have calculated, we will divide it by root 3, or we will divide 192.45 with root 3. So how much we will get? We will get 111.11 amperes, correct? So this is our primary current I1, okay. So what we are doing? Just calculating the current as we have to calculate in 3 phase, and then we have to take a reminder of whether it is delta or star and what will happen to the line and phase current. Now when it comes to the secondary current, okay, so secondary side is star side. So what will be the line current? The line current will be S upon root 3 VL, okay. What is S? Same, 1000 kVA divided by root 3. What is voltage on the secondary side? Root 3 kVA. So how much we will get? We will get 33.33 amperes. This is going to be the line current, okay. And this side is the star side. In star there is no line and phase difference between the current. So the same will be the phase current. So I2 will be the star side phase current, and it will be same as the star side line current, and that you have calculated, which is 333.3 ampere, correct. So in this way we have calculated the required current. Now coming back to the same formula, which is copper losses. So what will be the copper losses? So it will be 3I1 square. What is I1? 111.11 square R1. How much is R1? 0.20 plus 3 times I2. I2 is this much of current and R1 is 0.011, right. Now once you will calculate, the copper losses are coming 11.07 kilowatt. The answer that I have done is 11.07 for the copper losses. So have a look. Now we have calculated the copper losses. So half the job is done, okay. Now we have calculated the copper losses, okay. After that what we have to do? Nothing, okay. As we used to do in case of efficiency, same we will be doing here. So efficiency will be S2 cos phi 2 divided by S2 cos phi 2 plus iron losses plus copper losses into 100, correct. Full load means M is 1, so I have taken M here 1, or you can write M, no problem, M square PCFL, because full load, so it will be 1. Now just put all the values, okay. So SM is 1 into S2 is 1000 kVA into cos phi 2, we have to calculate at unity power factor. So same data we will write here, 1000 into 10 to the power 3. Iron losses are 10 kilowatt, right, plus copper losses are 11.07 into 10 to the power 3. Correct, into 100. Now when you will calculate the efficiency, it is coming 97.93%. 97.93%, which I can see Medha is getting and Bindu is also getting. Very good. Very good. Okay. So just see, this is a 3-phase question, 3-phase transformer question. Now majority of the student will just see that it belongs to 3-phase transformer, they will ignore it. But what is there for 3-phase transformer? Nothing like that. Okay. Same efficiency formula we have applied. We have calculated losses, and for that we need current, and this is the way we have calculated current. So I hope that this question is clear to you people, right? And you also are getting same answer. Very good. Now moving towards the next question. So see the next question. Okay, if the primary line voltage rating is 5 kV on the star side of a 15 kVA star delta transformer, the per phase turns ratio is 4:2, then the line current rating of the secondary side is what? Okay, and your time starts now. I know that you can solve this question, so I am giving you 2 minutes for that, and your time starts now. Tell me the correct answer for this question. Okay, we have a star delta transformer, one side ratings are given, transformation ratio is given, the line current rating of the secondary side will be what? What is going to be the line current on the secondary side is what we have to calculate, right? So do it. Let me see that who can give the correct answer for this question. This is the last question that we have from the transformer, and these are the topic which I find important for the current exam. Okay, losses, efficiency calculation, and some calculative questions from 3-phase transformer, right? Definitely you will get any one or maybe 2 questions from the same concept. So in this way, by solving these questions, we have just refreshed those concepts, right? Nobody is getting any answer. Okay, let's see what is given to us. We have a star delta transformer, right? A star delta transformer. Primary is star, secondary is delta. So primary side voltage rating is 5 kV. Secondary side voltage rating we don't know. Okay, and the rating is given 15 kVA. Power rating is 15 kVA, that is for both the side, and the transformation ratio is 4:2, right? Then the line current rating on the secondary side will be, what is going to be the line current rating here? Okay, that is what we have to calculate. Line current on the delta side. Meda is getting answer as A, 3.46. Okay, let's see. So we have been given the ratio N1 over N2, and what is going to be the ratio? 4:2, correct? 4:2 is the ratio. Now let us calculate the current on the primary side. Okay, so if we calculate the line current here, it will be S upon √3 VL, okay, or 15 kVA divided by √3 into VL, which is 5 kVA, correct? So how much we are going to get? The line current from here will be √3 ampere, correct? Are you getting √3 ampere when you have calculated the primary current? Correct? √3 amperes. And this is the star side. So on the star side, okay, whatever is the line current, same will be the phase current, and both are going to be what you have calculated, correct? Okay, now see, after that, if you will apply that phase current on the delta side upon phase current on the star side, okay, so secondary to primary current ratio, it will be what? N1 upon N2, correct? N1 upon N2. I2 upon I1, okay, this is the secondary side current, I2 upon I1, this will be N1 upon N2, correct. Now from here when you will calculate that what is going to be the phase delta current, so it will be N1 over N2 into star side phase current, correct. So N1 upon N2 is 4 by 2, and what is this current you have calculated, it is root 3. So you will get 2 root 3 ampere, right, 2 root 3 ampere. This is the phase current on the delta side, okay. What we have to calculate is the line current on the delta side, okay. So tell me the line current on the delta side. Line current and phase currents are different. On the delta side will be root 3 times the phase current on the delta side. So root 3 times 2 root 3, then what will be the answer? 6 ampere. I think you have not calculated the line current, right. On the delta side, line and phase currents are different. So whether 6 is answer or 3.46 is the answer. Tell me guys, Bhavani, Meda, what is the correct answer? 2 root 3 means 3.46. I think you are getting from that, right. We have to calculate the line current on the delta side, so you have to multiply with root 3 as well, correct. So now answer will be what? Answer will be 6. Got it? And what you have calculated is also there in the option, so be very careful. You all have calculated phase current, okay, very good. So with 3 phase things, na, just be very careful what has been asked, line or phase, correct. So these are the top 7 questions that I feel out of these questions or similar kind of question will be the part of the upcoming GATE exam, right. So what I can see that you people are having a very good practice of these topics, so you are in a very good touch of preparation, okay, very good. So I hope this question is clear. Now it comes the induction machine, okay. Weightage is around 3 to 4 marks, okay, and practice the last 10-year PYQs, because they are not going to give you new question. Many a times they have repeated the same concept of those PYQs, okay. So practice PYQs as much as you can from induction machine. If I talk about important topics whose formulas you can practice very well is slip and power calculations, okay, the power flow in induction machine, equivalent circuit, right, and then starting and speed control. Got it? So these are the important topics, and here is the first question that I have, right. A 6-pole 50 Hz 3-phase induction motor, 6-pole 50 Hz 3-phase induction motor running on full load develops a torque of 150 Newton meter at a rotor frequency of 1.5 Hz. Fr is 1.5 Hz. The mechanical torque lost in friction, is 10 Newton meter. Okay, so what will be the mechanical power developed? Mechanical power developed will be the output power plus the power lost, or 160 Newton meter. Then the ratio of rotor copper losses to the mechanical power developed. Rotor copper losses to the mechanical power developed will be what? This is what you have to calculate, and I am sure that you people can very easily solve this question, right. So let me give you 2 minutes and let me see who can solve this question. Hello Kiran, how are you? So calculate this ratio, copper losses with respect to the mechanical power developed. Okay, how much will be the ratio? How's your preparation going on? It's good. I know what you people are doing. You are calculating copper losses first, okay, the value of copper losses. Then you might be calculating PMD. PMD is given to us, okay, and then you are calculating the ratio, right? And the copper losses that you might be getting is 0.502 kilowatt, right? And that is why it is taking a lot of time of yours, right? But you know, you can solve this question easily. How? We know that the ratio of air gap power to the rotor copper losses to the mechanical power developed is 1:S:1 minus S. Out of this, we have to calculate the ratio of PRC to PMD, and that will be simply S/1 minus S. So to calculate this ratio, we need the slip only, right? And you can see the slip is given to us. How we will get the slip value? Fr equals to S into F. So S will be equals to Fr over F, and Fr is given 1.5 and F is given 50. So I think you will get 0.03, right? Then once you will put here 0.03 upon 1 minus 0.03, then I think the ratio will come 0.03. So answer will be B, right? Now tell me that how many of you have done exactly in the same way, and how many of you have calculated the copper losses first, then mechanical power developed, then you have calculated ratio, right? So you may waste your time, but think wisely. We have this ratio already, so this ratio is S upon 1 minus S, so we need the slip value only, and through the SIP we can very easily get this, right? So how many of you have calculated the numerical value of copper losses? Is there anyone, or you have done exactly in the same way? If you might have done in the same way, it could have been solved in 30 seconds only, right? Okay, so I hope that this question is also clear, and it is a very good question. Similarly, you may be asked to calculate other ratio as well. Now have a look over this question. A 25 horsepower 6 pole 50 hertz 3-phase induction motor. Let me write the data. So 25 horsepower 6 pole, right? Output power is 25 horsepower 6 pole 50 hertz 3-phase slip ring induction motor runs at 960 revolutions per minute. The rotor speed is 960 RPM. On full load with a rotor current per phase of 35 ampere. Wow. So I2 rotor current per phase is also given to us, allowing 250 watt for the copper losses in the short circuiting gear. Now see it, allowing 250 watt for the copper losses in the short circuiting gear. These copper losses are the additional losses that are happening in the short circuiting gear, right? And 1000 watt for mechanical losses. The resistance per phase of the 3-phase rotor winding will be, we have to calculate that what is going to be the resistance, right? What is going to be the resistance, right? So your time starts now. Let me see that who can solve this question. It's not about solving the question, it's about putting the right data as per the given case. Okay, so let me see that who can reach to that point, and your time has already started. the way the data is given has some difference. Okay. We have to calculate that what is going to be the rotor resistance here. Okay. These copper losses which are given are occurring at the short circuiting gear. Okay. Okay, so let's see that how we will approach for this question. It's a different question and it's an important one, right? So we know that PRC, rotor copper losses, are S upon 1 minus S times PMD, right? When it comes to PRC, copper losses are occurring in the rotor resistance, right? So copper losses occurring in the rotor resistance will be written as 3I2 square R2 plus additional copper losses which are occurring in the short circuiting gear. Okay, it is on the gear, is also given, which is 250 watts, right? Now S, what will be the S value? So let us calculate S first of all. Okay, so what will be the NS? NS will be 120 F over P. So 120 into 50 upon 6 will be 1000, right? Now when you will calculate S, which will be NS minus NR over NS, so 1000 minus 960 upon 1000, so you might be getting 0.04 per unit, right? This is the value of slip. So 0.04 divided by 1 minus 0.04. Now mechanical power developed. Okay, what is going to be the mechanical power developed? So mechanical power developed, okay, let me write here, PMD is basically equal to P output plus P losses, right? PMD will be P output upon P losses, or let me write once here the complete formula. So S upon 1 minus S, it will be P output plus P losses in friction. Got it? Now 3, just put the values. I2 is 35 per phase, square R2 plus 250 is equals to 0.04 upon 1 minus 0.04. P output will be 25 horsepower. So 25 into 746 kilowatts plus the losses in the mechanical power. Mechanical losses are 1000 watts. Okay, so just see, in this equation you have only one unknown, and that unknown is the R2 value. So once you will calculate it for R2, you will get 0.154. Okay, 0.154 ohms, and that will be the answer. Got it? So you might have calculated PMD, okay, with P output plus P losses, but you might be having one difference here. Okay, so copper losses occurring in the resistance is normally given by 3I2 square R2, but they have given one additional data that occurring in the short circuit gear, copper losses occurring in short circuit gear is 250 watt. So total copper losses is this much normally occurring plus this additional losses, right? And then you will calculate R2. So isn't it a very good question, a confusing one? So now you have a practice of that as well, and this relation is very important. Got it? So how many of you understood this question? Tell me. Anybody having any doubt? No, so these are the questions involving the slip calculation, these are the questions involving the power flow, right? These are the questions involving the power flow. So you are getting a practice of that part. I hope it is clear. Moving towards the next question. Now, question related to torque and slip. Okay, a 746 kilowatt. So 746 kilowatt, 3-phase, 50 hertz, 16 pole induction motor has a rotor impedance. Okay, so rotor impedance, which is R2 plus jX2, is given how much? It is given 0.02 plus j 0.15. That means R2 will be 0.02 ohms and X2 will be 0.15 ohms. Full load at standstill, full load torque is obtained at 360 rpm. Okay, so full load speed is 360 rpm. The external resistance per phase to be inserted in the rotor resistance to have maximum torque at starting. We want to have maximum torque at starting, and your time starts now. It's a very important, very popular type of question and an easy one, right? I think you can solve this question. We have to calculate the maximum torque at starting. So maximum torque is occurring at starting. Okay, mind these words. Come on, you can calculate this answer. Okay, we have to calculate that what is going to be the extra resistance that we are going to add to obtain this condition. Last 20 seconds. So just see, they are saying that we are getting maximum torque at starting. Okay, so what is the condition for getting maximum torque? Condition for maximum torque. What is the condition for maximum torque? That the slip should be R2 over X2, right? The slip corresponding to maximum torque should be R2 over X2, right? Now, what they are saying that we are getting the maximum torque at starting. Okay, so at starting, what is going to be the slip? At starting, your speed will be 0, so your slip will be almost 1. Okay, so now we are getting maximum torque at starting, so this value will be 1, right? And we have inserted extra resistance in the rotor circuit, right? This is what we have to do here. So what is the extra added resistance is what we will be calculating. R2 value is 0.02 plus this small r we have to calculate. X2 is 0.5. So I think R will be 0.13 ohms, right? R will be 0.13 ohm, which Shreyas is getting. Meda, how you are getting 0.48? How you are getting 0.48? It will be 0.13, which Shreyas has got. Very good, Shreyas. So is that understood? Okay. So this is also an important topic, condition of maximum torque, right? So this is a short version. You know, you may get questions like this in which you might be writing this as well. R2 dash by S equals RTH square plus XTH plus X2 dash square, right? This is the full formula from which, when we have neglected RTH, when we have neglected XTH, the Thevenin's equivalent resistance and reactance, then we are getting this reduced formula. So this is the full version of formula. So this time we have asked a question in which we have neglected the stator model. So we have applied this small formula. If suppose stator model is also concerned, taken, RTH, XTH values are given, then you might be using this formula, right? In this formula you could have written R2 dash plus R dash here, okay, and then you might have calculated R dash, and then they could have asked you that this will be the R dash, and you have to refer it to the secondary, then it will be R, okay. You can practice questions like this. They have already been the part of GATE exam, okay, so they are available as PYQs. You can practice those PYQs, those are also important, but this topic is very important. You will definitely get a question from this topic, right? So answer is 0.13. Meda, are you getting 0.13? How you are getting 0.48? And Bhavani, Bindu Sri, Sonali, what are your answer? What is your answer? So I hope this is clear, okay. You will find questions involving the same topic, but this formula are given in PYQs. Practice those PYQs, those are very important, okay. There are huge chances that you will get similar kind of question in the exam, right? Now moving towards the next question. So see this one, question 11. An auto transformer starter for an induction motor is required to start the three-phase induction motor, and they have given that the rotor is the stator is having a star connection, okay. The stator is having a star connected. Normally the stator of the induction motor is delta connected, but they have mentioned that it is star connected, right, with 40% of the full load torque, okay. So we have been given that starting torque to full load torque, this ratio is 40% or 0.4. The short circuit current of the motor is 5 times the full load current. So short circuit current is 5 times the full load current, and full load slip is 0.035. So SFL is 0.035. The current drawn from the mains as a fraction of full load current, okay. Current drawn from the mains, okay. So we are using auto transformer starter. So current drawn from the mains means we have to calculate the auto transformer current, right? So we have to calculate the starting auto transformer current. This will be the current drawn from the mains, and we have to calculate it in terms of full load current, right? This is what is given to us. So first of all, apply the formula. So what starter we are using? We are using auto transformer starter, right? So for auto transformer starter, you know that starting torque to full load torque this ratio is what? This ratio is x square, the auto transformation ratio, times ISC upon IFL square into SFL. Correct? This is the formula, general formula. Okay. If it is a star delta transformer, we know that this x square becomes 1 by 3. Okay. So from this formula we have been given so many things. So first of all, apply this formula. Starting torque to full load torque ratio is 0.4. X square, the auto transformation ratio, we don't know. ISC to IFL will be 5 square and SFL is 0.035. So from here you can calculate the auto transformation ratio x, and x might be coming 0.676, right? Then just see, normally our stator is delta connected, but they have mentioned that it is star connected. Okay, so we are in such a situation. Just see, we have auto transformer. If you will draw the figure, everything will be clear to you. We have auto transformer, okay, and in auto transformer this voltage is V1, okay. Then what voltage our motor is receiving? Motor stator is also star connected. Just like this, okay. So if this voltage is V1, then how much voltage we are getting here? We might be getting only x V1 voltage here, correct? Because transformation ratio is x V1, that the current here, which is ISC, will be x V1 upon Z. Let's suppose this impedance is Z, okay. Right. Now what we have to calculate, that how much is the current flowing here, how much current we are drawing from the line. Okay, so just see, KVA here must be equal to KVA here. Okay, so if you will apply this simple condition that KVA balance, okay, then see what we can get. Okay, so KVA on the auto transformer side will be what? It will be V1 and current is IS auto, right? KVA on this side will be what? What voltage we are receiving here? What voltage we are receiving here? We are receiving BN cars. How can I access your previous video? It's very simple. Just visit our our YouTube channel. Okay, go to the playlist. Whatever video I have taken, you will find those. Right. Now, so what will be the KVA on this side? Okay, so KVA on this side will be what voltage we are getting for the motor, what voltage it is receiving? X V1, okay. And what is the current? What is the current? Starting current. Let me write starting current of motor, okay. In this way, if you will apply this, then see what will happen. So V1 and V1 you will cancel, and IS auto, this will be X times, what is IST, or IST is basically ISC. So what you will be getting is X V1 by Z, okay. So you will get X square V1 by Z. Got it? Acha, let me do a change. This is basically IST, okay, and X V1 by Z, if we are writing, then we can write it X times ISC, okay, because ISC is V1 upon Z, right. So we will get X square ISC, correct. Now X square ISC, just put the values. So you have calculated X is 0.676. So 0.676 square into ISC is given 5 times the full load current, Okay. Once you will calculate this, okay, then you will be getting 2.28 times the full load current. Okay. So what they are asking, the current drawn from the mains, okay, current drawn from the mains means auto transformer current is how much fraction of full load current. So it is 2.28 times the full load current, 2.28 times the full load current. Got it? I hope it is clear. So in class you might have practiced for delta connected load. You are very habituated of doing those calculations, even you have direct values, right? But just go through the question carefully. They have given that your stator is star connected. So if it is star connected, you have to do like this. Okay. By the way, whether it is star or delta connected, you might have applied this condition to get whatever is the line current. Okay. Same way you have to do here. Okay, whatever the load is. So is that problem understood? Give me a reply, guys. Bindu, Medha, Shreyas, Bhavani, Kiran. Is that question clear? Okay. So we have done questions related to speed calculation, we have done question related to power flow, we have done question related to starting of the induction motor, okay, and the last question was related to torque and slip. Okay, all these are important topic. Many questions have already been asked from this topic. Practice those PYQs as much as you can. Okay, and there is a huge probability that you will get exactly same concept getting repeated, only the values will change, the formula will be even the same, right? Now after that, one question I have from induction motor, okay, and this year I am expecting that they will ask a question related to capacitor calculation, and what is given in this question is a single phase 230 volt 50 Hz 4 pole capacitor start induction motor has following stand still impedances: main winding 6 plus J4, auxiliary winding 8 plus J6. The value of starting capacitor required to produce maximum torque at starting. Okay, maximum torque at starting. If this condition is given, then the phase angle of auxiliary winding is 90 minus the phase angle of main winding by 2 is what you have to apply. Correct? Under this condition, to have maximum torque at starting, auxiliary winding phase angle is 90 minus main winding phase angle by 2. Now how you will calculate auxiliary winding capacitance? Just see, auxiliary winding, so ZA is 8 plus J6, okay, means it will be like this, 8 plus J6, and we will be adding a capacitance here. So R plus JXL and minus JXC, right? In auxiliary winding we will be adding a capacitance. So how we will write it? Tan inverse XC minus XA, okay, this is RA, this is XA, XC minus XA over RA, this is equals to 90 minus phi m. How you will calculate? In main winding we have only resistance and inductance, Rm and Jxm. So tan inverse Xm over Rm only you have to do, divided by 2. Correct? Now tan inverse Xc we don't know, Xa is how much? It is 6 divided by Ra is how much? 8. 90 minus tan inverse Xm is 4 and Rm is 6 divided by 2, right? If you will solve this equation for Xc, then Xc will be 10.24 that I am getting, okay, then equate it to 2 pi Fc and calculate the value of capacitance. Capacitance might be coming 311 microfarad, right? Capacitance might be coming 311 microfarad. So this is one such case in which maximum torque at starting is asked, then you have to apply this condition. In a normal case, they may give you certain other conditions. Okay, so what you have to do, if suppose in normal case you have to calculate that what is going to be the value of capacitance, okay, then they will give that what phase difference they want to adopt between phi a and phi m. So that phase difference will be given, it might be 90, so phi a plus phi m will be 90. So then you have to apply those conditions. Okay, otherwise if maximum torque is asked, you have to do exactly in the same way. So you have to remember this formula, correct. So this is what I have from induction machine. Okay, so transformers are done, induction machines are done. Now there comes the DC machine, right. In DC machines there are lot of theories. Okay, what you can do in this last time, if you have covered that theory, very good. Otherwise you can just focus on the numerical portion of DC machine, because if you will revisit all the PYQs, you will find that they are only interested in numericals. From last 10 years they have asked 99.9% DC machine questions as numerical. It will be a very good exercise that if you will practice all those 10-year PYQs, because same type of PYQ is going to be repeated. Average weightage is around 2 to 3 marks. You may get 1 or 2 questions from this topic, and that will be very easy. So don't ignore DC machine. Important topics are EMF and torque equation, starting and speed control, right. Ignore all the theory part, just go through the equivalent circuit, learn how to apply KVL and KCL, and jump into the question and practice as many as you can. This is the first question that I have. A 4-pole wave wound 1200 RPM DC machine has 50 slots with 20 conductor per slot. So let me write the data. 4-pole wave wound. So if it is wave wound, the number of parallel path will be 2 only, right. Speed is given 1200 RPM and it has 50 slots with 20 conductor per slot. So number of conductor will be 50 into 20 or 1000 conductors. Now if the induced voltage in the machine is 510 volt instead of 540 volt, so in one such case the induced voltage, in one case induced voltage is given 510, in the other case the induced voltage is given 540, then the leakage flux will be, so at that time the flux was phi1, at that time the flux was phi2, the leakage flux is what you have to calculate, means you have to calculate phi2 minus phi1, right. So you need the formula for E. So formula for E is P phi n z by 60A, right. So in first case it is 510, number of poles are 4, phi will be phi1, speed will be 1200, z will be 1000 divided by 60 into A, which is 2, right. So from here when you will calculate phi1, everything is given. When you will calculate phi1, what I am getting is 0.0153 Webers, right. Then apply the same formula for the second case when the voltage is 540, then it is 4, it is phi2, everything will remain same, only phi2 and E will change. Okay. Then when you will solve it for phi2, the answer that I am having is 0.0162 Webers. Okay. Then leakage flux will be phi2 minus phi1, because phi2 is more than this, then you will get 0.9 milliwebers, correct, and answer that we have to give is in milliwebers. So 0.9 milliwebers. I hope that you are also getting the same answer, 0.9 milliwebers. Right, Meda, you are getting 4.2. 0.9 Just cross check the solutions. Bindu is getting 0.9. Okay, right. So I hope that this question is clear. Okay, it's an easy one. Okay, now have a look over this question. Okay, a 230 volt 1150 rpm DC motor equipped with a compensating winding has Ra equals to 0.2 ohm when operating as a shunt motor. The rated output is obtained with a line current of 52 ampere and the field current of 2 ampere. The same constant torque is to be applied when same constant torque remains constant, right, is to be applied when the machine operates as a long shunt cumulatively compound motor at this load condition. The series field winding resistance is given and contributes a 50% increase in the flux pole. The speed of the motor will be, just see, whenever we have to calculate speed, you have to apply these formula. E2 upon E1 is phi 2 upon phi 1, N2 upon N1, right. Whenever we have to calculate speed, we have to apply these formulas. Now what you can see that flux is 50% increase. So flux will become 1.5 times phi 1. Okay, N1 is given. How much is N1? N1 is given 1150 rpm. We have to calculate N2, right. So for that we need E2 upon E1. Got it? E1 will be the voltage when the machine is running as shunt motor. E2 will be the voltage when the machine is running as long shunt motor. So we have to calculate these two things. Okay. So case number 1, when it is running as shunt motor. Okay. So the best strategy is to draw a motor. So draw a shunt motor. So if we draw the shunt motor, okay, we are giving voltage which is 230 volt. Okay, this is our V, right. It is having Ra equals to 0.2. Ra is given 0.2 ohm. Okay, rated output is obtained, what they are writing, with a line current of 52. Okay, so the line current is given 52 ampere and the field current is given 2 ampere. Then how much is this current? Obviously 50, and that will be our armature current, right. Now apply KVL. So V is equals to E plus IARA, right. V is equals to E plus IARA. Okay, but we have to calculate what? We have to calculate E. So better we apply E equals to V minus IARA. So E1 equals V minus IA1 RA. So V is 230 volt minus current now is 50 and RA is 0.2. So how much we will get? 220, right? Yes, 220 volt. Correct? Now they are saying that the same machine is operated as a long shunt machine. Okay, so if it is operated as a long shunt machine, then what will be the current that it is carrying? We have to calculate that. Okay, so for that we have been given that torque remains constant. Okay, torque remains constant means T2 upon torque is given constant in both the conditions. So T2 upon T1, which is phi 2 upon phi 1, IA2 upon IA1, because torque is proportional to phi into Ia, right. So this is given constant. So we will get 1 here. Phi 2 upon phi 1 will be 1.5. IA2 upon IA1. IA1 is this current, okay, which is 50. So what will be our new armature current? Our new armature current will be 50 upon 1.5, right. So the new armature current will be 33.33. Right. In this way we will calculate the new armature current. Got it? So we have calculated the new armature current. Right. Now we have to calculate that what is going to be the E2 value. Okay. So case number 2, the long shunt motor. So draw the long shunt motor. How we will draw the long shunt motor? We will be having a series resistance. Okay, so it has RA which is 0.2. It will be having series resistance. This is the shunt resistance. Okay, here is the voltage, and right now what current it is drawing, we know that IA2 is known to us. Okay, so if we apply now E2 equals to V minus IA2, and it will be not only RA, we will be getting RA plus RSC. So 230 minus the new current which is 33.33, RA which is 0.2, and RSC is given 0.05. Right. So from here we will be getting the E2 value as 221.66. Right. Now E2 and E1 are known to us. Right. E2 and E1 are known to us. So from this formula, if we calculate the value of, N2, then what we are going to get? So N2 from this formula will be E2 upon E1. So 221.66 upon E1 is 220, right, into phi 1 upon phi 2, which will be 1 upon 1.5, into N1, and how much is N1? 1150. Okay. So when you will calculate it, the answer that we are getting is 772.45 RPM. Got it? Which Medha and Bhavani are getting. Very good, very good. If you can solve this question, you can solve any question of the GATE exam. Bindu, why your answer is different? I think you have done some mistake, right? So just cross check where you have mistaken. Right. So this is how we will go for this question. Okay. For DC machine question, read between the lines. What is constant, what is changing. Okay. In most of the cases, you only have to apply this equation, or either you have to apply this KVL equation, that's it. And you should know the equivalent circuit of a particular motor. If you don't know that how the long shunt motor is to be drawn, you will not take RSC value here, and that will give you a wrong answer. Right. So be very sure about these questions. Okay. Then moving towards the next question. Have a look over this one. A 20 horsepower 230 volt 1150 rpm motor has 4 pole 4 parallel armature paths and 882 conductor. Let us write the data. Okay. Speed is given 1150 rpm. Okay. Speed is given 1150 rpm, and it has 4 pole and it has 4 parallel paths, right, and it has 882 conductors, and the armature resistance is 0.2, and the field current is given 2.6 ampere when operated at a shunt motor. So it is the shunt motor. The efficiency of the motor is given as 86.96%. Then the rotational losses will be, wow, what a question. We have to calculate the rotational losses, and your time starts now. Let me see that whether you can solve this question. Efficiency is given, and we have to calculate that how much will be the rotational loss, right? Come on, try it, you can do it. Let me give you a hint that rotational losses will be mechanical power developed, right, minus the output power. When you will add output power plus rotational losses, then you will get mechanical power developed. Got it? So first we are getting mechanical power developed, then some losses are happening, and finally we are getting the output power. Last 20 seconds. Okay, let's see how we will solve this question. So P rotational will be P mechanical power developed minus the output power. Mechanical power developed, if you have to calculate, you can calculate like this: EA into IA minus P output. P output will be, P output is given, right? Or yes, it is 20 horsepower. Meda is getting 862.52. Okay, I am getting 603.2. Okay, let us check whether my answer is correct or your one, right? So just see, neta will be output over input, right? We need to get EA. Now neta is how much? Neta is given how much? Neta is given 86.96, so 0.869 is equals to output. Output will be 20 horsepower. So 20 into 746 divided by the input, right? So from this exercise you will get your input. Got it? So the input will be that I am getting is 17,157.31 watt. Are you getting this input, right? Now after getting this input, equate it to V into IL, right? Input will be V into IL. So from here you will get the line current. Line current will be 17,157.31 divided by V, and V is 230 volt. Then the line current value that you will be getting is 74.6, approx 74.6 amperes, correct? Then what type of motor it is? It is a shunt motor. Line current value is given, we have calculated, field current is given, so we can calculate armature current, which will be line current minus the field current. 74.6 minus how much is the field current? 2.6. So we will get 72 ampere. Okay. So we need IA, we have IA. Now we can calculate EA, which will be V minus IA RA. So 230 volt minus IA, which is 72, and RA 0.2. Okay, so EA will come to 15.6 volt, right? 215.6 volt will be this value. Then come here and just write down the values. EA is 215.6, IA which is 72 minus output will be 20 horsepower, 20 into 746, when you will calculate this, then I am getting 603.2 watts, and that will be the answer, right? Oh, I added PMD and P output. Be very sure, okay? First motor will generate some mechanical power, then there will be losses, finally you will get output, right? Right? So this is how you have to solve this, because they know that student can do mistakes, that's why they are very much interested in giving these questions, okay? Many students will do mistake in applying this formula, correct? This is how we have to approach for this question. But I am very happy that you people are trying, okay, and many answers you are giving, many questions you are able to solve. So this is very good, okay? That means your skill set is fantastic. So I hope that this is done, okay? Nobody has a problem in this question. Can we move to the next question? Now see this one. A separately excited DC motor is operating at 1500 RPM, draws 120 ampere from the line at terminal voltage of 230 volt. Terminal voltage is 230 volt. Line current will become the armature current because it is separately excited motor, is 120 ampere, and the speed is 1500 RPM. Right, and let me call this N1. The armature resistance between the terminal is RA is 0.075. The speed of the motor, what will be the speed of the motor when the torque is 500 Newton meter for the same excitation, right? So when the torque is this, at that time what will be the speed? Okay, this is what you have to do in this question. So how to approach for this one? How to approach for a question like this? Okay, whenever we have to calculate the speed, which then it is only possible, just see, nothing is said about phi, and it is separately excited motor, phi will be constant. So we will be applying E2 upon E1 equals to N2 upon N1. Speed can only be calculated through this formula. For this formula we need E2 and E1. Is there any problem in calculation of E2 here? No, we can very easily get, okay. So if I have E1 will be V minus IA1 R1 RA, right? So 230 minus, what is our armature current? 120 and RA 0.075. When you will do the calculation, you will get it 221, right? So we know this. Now in order to calculate E2 for the second case, we need to have current, right? We need to have current. How we will get current, right? How we will get current is a big question. Now if you want to calculate current, that is possible through the ratio of T2 to T1, which will be, because phi is constant, so it will be IA2 upon IA1. Just see how I am guessing that what we have to calculate, how we can approach. T is proportional to phi into I, right? T is proportional to phi into I. So phi is constant, T2 upon T1 will be IA2 upon I1. IA1 we know, IA2 we can calculate, T2 is known, T1 is what we have to calculate. So do we have T1? So how to calculate T1 is a big question, okay. So to get T1, what we will do? T1 in case of first case, okay. So T1, you know that PMD is equals to what? EA into IA, and PMD will be omega into tau, right? So EA into IA, okay. Here it will be EA1 IA1 omega 1, okay. Omega 1 will be 2 pi N1 by 60 into T1, right? Do we have all the value? EA1 is 221, IA1 is 120, 2 pi N1 is how much? 1500, upon 60 and T1. So from here you will get the value of T1, and that I am getting is 168.91. Right. Now after that, if you will apply T2 upon T1 equals IA2 upon IA1, okay, then what will happen? T2 is given 500, T1 is given 168.9, IA2 is what we have to calculate, IA1 is 120. So from here you will get IA2, and that I am getting 355 ampere. Right. Once you have calculated these things, okay, now we can calculate EA2. Okay. So what is going to be EA2? EA2 is going to be V minus IA2 RA. So 230 minus 355 into RA remains same. So I am getting EA2 as 203.375 volt. Okay. Then through this relation, what is going to be my N2? It is going to be E2 upon E1 into N1. So now apply. E2 is how much? 203.375. E1 is 221. N1 is 1500. Okay. So when you will solve it, you will finally get your answer. Okay. And that speed is coming 1380.37 rpm. Okay, and this will be the answer. 1390 you are getting. Okay, I am getting 1380. Right. So whenever we have to calculate speed, we have to apply this formula. Now in this formula, E1 we can calculate with the given data, E2 cannot be calculated, right? In order to calculate E2, we need to have IA. How to get IA? IA currents can be calculated through the torque relation. T2 is given, T1 we can, whenever we have to calculate torque, we have to apply this condition, right? For the calculation of torque, we have to apply this condition, we will get torque. Torque is known, current will be calculated, current calculated, EA2 calculated, apply this relation and get the problem done, right. So this is a sequence that we will be following in all the questions of DC machine, correct. Most of the questions will be solved through this only. So I hope it is clear. Is that clear? Okay, shall we move to the next question? Anybody having any problem in this question? Is that clear, guys? Give me a reply. Can we move to the next question? So when it comes to DC machine, it has become a procedure that you have to apply. Okay, in most of the questions you are doing exactly like the same thing. Got it? Is it done? Now see the next question, right? And this is the next question. A DC shunt motor is connected to 120 volt DC supply and is found to have a back EMF of 100 volt as 1500 rpm. It is connected to 120 volt supply and it is found to have back EMF of 100 volt at 1500 rpm. Right. The speed of this machine when it develops a torque of 50 Newton meter. So when it develops a torque of 50 Newton meter, at that time what is going to be the speed is what we have to calculate, correct. So now this time we have this data. What is the machine? Shunt machine. Okay, what is the difference between this question and the last question? In the last question also we have the same things, right, and IA is given for the first case directly, okay, but in this case the IA is not given, currents are not given to us directly and power is also not given, so we cannot calculate the current, and we cannot calculate, we cannot comment about the power. So it is the same question, but it cannot be done the way we have done earlier, right? Why? Because currents are not given, powers are not given, so we cannot calculate currents. Then what to do? Okay, then see, E is given to us, and E is K phi omega m, right? E can be written as K phi omega m. Similarly, torque can be written as K phi IA. So you can see K phi is coming in both the formulas, same constant. Okay. So if we apply first this formula, E equals to K phi Im. So E is given 100. Okay. Let's suppose K phi we want to calculate. Omega m will be 2 pi. The speed N1 is 1500 rpm by 60. So from here you will get the constant K phi. Okay, and this constant will be coming 0.636, right? This constant will be coming 0.636, right? Now apply this one. So we know that in the second case T2 is how much? 50 Newton meter, and T2 can be written as K phi IA2, right? Now it is 50, K phi is 0.636, IA2, so you will get IA2 which is 50 upon 0.636, or it is coming 78.61 amperes, right? Now you can see that this was even, so you can calculate now EA2, which will be V minus IA2 RA, right? So how much is V? 120 minus 78.61, and the RA is given 0.3. So from here you will get EA2 which is coming 96.41, right? Whenever we have to calculate speed, we will be applying this relation, as you know. Okay, this is shunt motor, so flux is constant because nothing else is mentioned about that. Now put the values. E2 96.41, E1 100, speed 1500. So new speed you will calculate as 1446.15 rpm. Got it? Very good, Medha. So just see, again we have applied the same formula. To apply this formula we need the value of E2. E1 was given to us. How to calculate E2? E2 requires IA2. How to get IA2? Through the torque. Okay. So this problem and the last problem, they are almost similar, but both of them are done in a different manner. Okay. This problem we have done in this way. Last problem we have done in a different way, because currents were given, power were given, so we can calculate other things. Here currents are not given, so we cannot calculate. So here we have to apply this method, right? So I hope that this question is also clear to you people, right? Then after that, let's see this one. Question number 18. A 50 kilowatt 500 volt cumulatively compound shunt, and long or short, it is long shunt generator. First question we are getting from generator is equipped with a diverter, delivers rated load. So what kind of generator we have? Cumulatively compound shunt generator, long shunt generator. Let me draw that. Long shunt generator is like this. Okay, I really like this question because in this question we have a lot of learning. So this is series resistance, this is shunt resistance, right? It will be having some armature resistance. Here is the, this is generator. So current might be coming from here, current will be going here, okay, and current might be coming out here, right? Now what they are saying that it is equipped with a diverter. Diverter is connected in the series winding like this. So it is equipped with a diverter resistance. This is RD. very good, and the voltage is 500 volt, correct. The current through the shunt and the diverter are 4 ampere and 21 ampere. This current is 4 ampere and current through the diverter is 21 ampere. Okay. Find the diverter resistance and compute the generator voltage, and they will be out of these. Okay. Diverter resistance value we have to find, and we have to find generated voltage, correct. So generated voltage requires the armature current. So can we get armature current? Yes, we can get that. So this is armature current, same will be the armature current here. Now we can get IL. IL will be P over V. How much is P? 50 kilowatt. And how much is V? 500. Okay, so IL will be how much? 100. Yes, it is 100. Correct. Then see, IA has IL plus ISH. So it is 100 plus it is 4. So we will get 104. Right. Then IA will be the current across the diverter plus the current across the series. So it is 104. It is 21. We will get ISC. So ISC will be 83 ampere. Correct. Then just see the diverter. Okay, the diverter and the series field winding both are in parallel. So if they are parallel, so the drop across them ID RD will be equals to the drop across the series winding. Okay. Now ID is 21 and diverter resistance we have to find. ISC is 83 and RSC is given 0.02. So when you will solve it for RD, you will get RD equals 0.079. Okay, or approximately it is 0.8 ohm. So you calculated it is 0.8 ohm. Now we need to calculate E. Okay, so what will be E? So E will be V plus IARA, right. E will be V plus IAR. It is generator, so KVL will be different. Okay, don't mistake while applying the KVL. So what is IA? 104, right, and how much is RA? 0.01. So you will get 502.7 volt as the value of E. Okay. If you will apply wrong KVL, you are not going to get answer, and that option is also given. So be very careful. It is generator. The KVL will be V plus IARA. Okay, this is a common mistake that students normally commits. Okay, don't do that. Got it? So this is how you will solve this question, right? I hope it is clear. Okay, and you people are also getting the same answer. So that's very good. Now see this question. Okay, the hysteresis and eddy current losses in a DC machine running at 1000 RPM are 300 watt and 200 watt. So hysteresis loss 300 watt, eddy current loss 200 watt. Okay, and both the losses are at the speed of 1000 RPM. Right. If the flux remains constant, then at what speed the total iron losses? At what speed the total iron losses will become half? Okay, so Pi will become Pi by 2. At what speed is what we have to calculate. Okay, Bindu is getting same answer, very good. So now can you solve this question? We have to calculate at what speed the iron losses will become half. Okay. So iron losses, which are hysteresis losses plus eddy current losses, so they are initially how much? 500 watts, right? They are initially 500 watts. Now you know that hysteresis losses are A into F, right? Frequency frequency means speed, so we can write it A into N1 as well, correct. Now hysteresis losses are 300 watt equals to A into N1. How much is N1? 1000. So from there you will get the value of A, which will be 0.3, correct. Similarly, eddy current losses, which are B into F square, or F is nothing but the speed, okay. Talking about frequency means talking about speed. So they are 200 plus B into 1000 square. So when you will solve it for B, you will get 0.2 into 10 to the power minus 3. So in this way you have calculated A and B. Whenever we are talking about stresses and eddy current losses, first of all we have to calculate these constant A and B. We have done that, right. Now in the second condition, what they are saying, that iron losses becomes half. Total iron losses were 500, so now they become half. Then what will be the speed? So again we will apply that total iron losses are hysteresis plus eddy current losses, okay. So 250, this is equals to A times N2 plus B times N2 square, okay, and A value is 0.3 N2 and B value is 0.2 into 10 to the power minus 3 N2 square. So when you will solve this equation for N2, you will be getting N2 as 516.3 RPM. One of the speed might be coming negative, that you may ignore, right. So C is the right answer, correct. Why we have done this question? You should know this concept. You should know this concept. If you know this one, you can solve this question as well. I hope it is clear, right. So guys, this is what I have from DC machines, okay. These are my important questions and important topics. All those important formula that I wanted you to practice, we have done those, right. Practice these questions and formulas and concept as much as you can, and you will surely get one question from DC machine, or maybe two questions, and you will be able to do that, right. Machine is a very important subject. If suppose you are scoring marks from machine, it is sure that you are going to get under 100 rank, right, because machine is a subject in which most of the students are not that much comfortable. So what is discomfort for others, if it is a comfortable one for you, you are leading towards the success, right. Now, so this is about DC machine. Now if I talk about synchronous machine, average weightage 2 to 3 marks. Important topics: cylindrical motor, cylindrical rotor or salient pole rotor, generator and motor calculation. Practice these questions. Practice how to apply KVL in case of cylindrical rotor motor and generator, in case of salient pole motor and generator, okay. You have to practice to apply these things. Effect of varying field means V curve and effect of varying load, okay, out of which this topic is very important. They are asking regular question from these topics, and we will also focus on these topics in class in this gate score booster. And this is the first question that I have from DC, from synchronous machine. Just see, a 3-phase 50 Hz salient pole alternator has per phase direct axis reactance, it will be X of D here, 0.8, and per phase quadrature axis reactance of 0.5, okay. So we have been given that the XD value is 0.8, XQ value is 0.5 per unit. Resistance of the machine is negligible. When they have written this line, thanks to them, okay, because neglecting armature resistance will reduce calculation to up to a very great extent. The per unit open circuit voltage for the full load and at a lagging power factor, we have to calculate E, okay, and the power factor is given 0.8, and they are talking about full load. So because you are doing calculation in per unit, you can take IA to be 1 per unit, right? And you can take V as a reference, and V can also be taken as 1 per unit. You can assume these two things from your side, right? Then we have to calculate E. So how to do this question? We are talking about what? We are talking about alternator. Okay, so alternator will generate the voltage EF, then there will be a drop in the armature resistance, right? Then there will be what? There will be drop related to the direct axis reactance, then there will be a drop related to the quadrature axis reactance, and this is how our KVL equation will be completed, and then finally we will be getting V. Okay, or I can write EF to be V plus IA RA, right, plus J ID XD plus J IQ XQ, correct? Okay, this is going to be our KVL equation. Right guys, this is going to be our KVL equation. Got it? Then if you will modify this, you can write it V plus IA RA plus J XQ. Okay, RA plus J XQ plus J XD minus XQ ID. Okay, how we will write it? If we divide IQ into IA minus ID, we can write this equation, correct? So now just see, if we write this one as EF double dash, so our equation will be E of F equals to EF double dash plus J XD. Acha, you know, when you have done this calculation, you can simply add this drop, because when you will draw the phasor diagram, you will find that they are in phase. Okay, so this is how you can calculate it. Okay, this is how you can calculate it. So we need to calculate EF double dash first, and which will be V plus IA RA plus J XQ, correct? Now RA is neglected, so we will get V plus IA or JIA XQ. Now V is 1 per unit. What will be IA? IA will be 1, okay, and power factor is lagging, so cos inverse 0.8. This will be our current, and XQ value is given 0.5, or you can write it 1 plus J 0.5, angle will be minus 36.86. If power factor is 36.9, okay, if power factor is 0.8, phi value will be 36.9, right? Then when you will solve it for EF double dash, then EF double dash might be coming 1.36, angle 17.1. Just follow the process that I am doing, okay? And EF double dash might be written as EF double dash angle del. You know, both EF and EF dash, they will be having the same angle del. Okay, so now we are getting the value of del. The value of del is how much? 17.1. The value of phi is 36.1. Okay, now EF double dash we have calculated. We need to calculate ID. Okay, so what is ID? ID is IA sin psi. Now what is this psi? Okay, so how to calculate the psi? So just see, it's very easy. You can calculate psi as per the power factor very easily. Just see, if we take V as reference, then current is lagging, so this will be our phi, and you can see that we have taken as reference phasor, so EF del angle is positive, so EF is leading, correct? This is del, this is the angle of EF, right? So EF and IA, the angle that EF and IA share is the angle sine. So what is sine? So sine, as you can see, for lagging power factor it is del plus phi. So now you can write the same thing here, IA, okay, IA sine sine, IA is 1, sine is del plus phi. So 17.1 plus 36.1, right? So when you will calculate it, ID will come 0.809, right? Now come back to the same formula, this formula. So from here EF will be EF double dash plus XD minus XQ into ID, okay, and you can ignore the angles, you can ignore the J, okay, because when you will draw the phasor diagram, this and this will be in phase, so ignore J, ignore angle. Now what is the EF double dash amplitude? It is 1.36. XD minus XQ will be 0.8 minus 0.5. ID is 0.809. So when you will solve it, you are going to get 1.6 per unit. Got it? So through this question, I have told you the complete process of how to solve these questions, right? How to solve this question. Del minus phi for lagging, that we will do in motors, not in generators, right? V you have taken reference, IA will be lagging, and in generators EF leads VA. Del is positive for generator, okay? Del is positive for generator, means EF leads VA. So EF and IA will have as angle sine, and sine will be then del plus phi. Got it, Medha? Okay, so complete procedure, how you have to approach for these things, I just told you. No need to memorize anything, right? And this is how you will solve these questions. Now we will solve one question related to motor as well. Okay, Medha, is that clear? It will be del plus phi. Very good. Okay, so I hope that this one is clear, right? How to approach is also clear. Okay, if you will practice question like this, surely you are going to solve one gate question. Now see one question from of this type. A three-phase synchronous motor draws 180 ampere from the line at 0.5 power factor lagging at rated load. Consider the same line voltage and load. The line current at power factor 0.5 leading will be. For this situation, you have to apply IA1 cos phi 1 equals to IA2 cos phi 2. So IA1 is 180 and the power factor is 0.5 lagging. IA2 we have to calculate, and the second power factor is 0.5 leading. So from here when you will calculate IA2, it will be 180 amperes. Okay, it is synchronous motor. So in synchronous motor, you know that if it is V, okay, and if this is EF, right, and if this is IA1 X1, okay, then if suppose first we have lagging current, then we have leading current, if suppose this is V, and if suppose this is the lagging current, if suppose this is the leading current, okay, then what will happen? We will be having EF IA1 axis, and this will be our EF1, okay. Then we can have EF2, okay, and this will be our IA2 axis, right. So what you can see, that if you are increasing the excitation, your current is becoming from lagging it is moving towards the leading like this. Okay. So if the excitation will be increased, current will be moving from lagging towards the more leading. In this way what it will maintain? It will maintain Ia cos phi as constant. It will also maintain this vertical line will also be constant. So it will maintain Ef sin del as constant. What is del? Del is the angle between V and Ef. Okay. So this is del 1, this is del 2. Okay. What you can see is that V and Ia share an angle phi 1 here, V and Ia share an angle phi 2 here. So Ia cos phi will be constant, Ef sin del will be constant. Got it? So if the field excitation is increased, current will move from lagging towards unity, then leading. If the field excitation is decreased, current will move from leading towards unity and then it will be lagging. Okay. This is known as effect of varying the field current, okay, or V curve. So I hope this question is clear. So many times they have asked question like this, and you should know that what will happen when we are varying the field excitation. When we are increasing, the power factor will move from lagging towards lagging towards unity towards leading. When we are decreasing the excitation, it will move from leading towards less leading towards unity towards lagging. Correct? So these fundamentals should be very clear to you. Ia cos phi remains constant during that, Ef sin del remains constant during that, because for power to remains constant, same power, same load, we are doing those things. Okay. And that they have mentioned. That is why we are able to apply these things. So I hope that this question is also clear. Okay. It's an easy question, but you should know about these conditions. They may ask indirect question related to this topic as well. Then I have taken this question, which is almost similar to a gate question. Okay. But I was not able to stop myself by taking this question, because I feel that this is very important. Okay. From the synchronous alternator, EMF method is very important. Okay. And EMF method, direct question can also be asked, or indirect question like this can also be asked. So what is given here is that a star connected 400 volt 50 hertz 6 pole synchronous machine gave the following open circuit and short circuit test result. Open circuit voltage is 440 line to line at field current of 1.8 ampere. So open circuit voltage is 440 volt, and this is line to line. Okay. What will be the phase open circuit phase voltage? It will be 440 divided by 3, and this we are getting for a field current of 1.8 ampere. When we are conducting the short circuit test, then the short circuit current is 10 ampere, but it is at a field current of 1.5 ampere. Right? What we have to calculate? We have to calculate the per phase synchronous impedance. Synchronous impedance is open circuit phase voltage divided by short circuit current, armature current, but for the same field current. But what we can see, that the field current is not same here. What many students will do, they will divide it. Some of them will forget to divide by √3. Some of them will do that and they will directly divide the data without looking that the field current are not same. Okay. So what we will do, just see, for field current, for IF equals to 1.5, what is IISc? Equals to 10 ampere. For IF equals to 1 ampere, it will be 10 by 1.5. Similarly, for IF equals to 1.8 ampere, this will be 10 upon 1.5 into 1.8. Okay. So what you are going to get? You will get a short circuit current of 12 ampere. Right. Now this is what we will take. Okay. Now this is what we will take. So we will put here 440 divided by √3, and the short circuit current will be 12 ampere. Okay. I think it is not visible. Let me write it here only. Okay, this is how you will calculate the currents, and after that ZS will be open circuit per phase voltage divided by short circuit current for the same value of IF. So, we have calculated it for the same value of IF. Okay. So, ZS will come 21.17 ohms. Correct? Is that clear? Always take care of what is given in DC in machines question. Okay. Sometimes you will directly do the things what you know, and that may be misleading, right? So, we have to see that it is for the same field current, and the field current is not given same. Okay. So, take care of these things, right? I hope that it is clear. Nobody has any problem in this. Now, after that, see this question. The direct axis and synchronous axis, quadrature axis reactances are, these values are given. XD is 1 per unit and XQ is 0.8 per unit. The armature resistance is neglected. Thank you so much. If this alternator is delivering rated kVA at unity power factor, so the power factor cos phi is given 1, sin phi 2 will be 0. At rated voltage per unit things are given, so you can take V as 1 per unit, you can take I as 1 per unit, this you can take. Then what will be the power angle? You have to calculate the del value. Okay, you have to calculate the del value, and it is alternator. Okay, let me take you the last question. So, if you have seen that we have derived this equation, okay, if you have seen that we have derived this equation, right, let me again write this equation. Okay. So, just see, I have written this equation here. Out of this equation, what I told you that it is like E double dash angle, EF double dash angle del plus J XD minus, or what I told you that we need not to write the values of J here. So, simply, or let me write, no issue. Okay. So, whatever is the angle of EF, the same will be the angle of EF double dash. Okay. So, what is EF double dash? EF double dash is V plus IA RA plus J XQ, correct? Now, RA is neglected, so we can write it JIA XQ. Okay. This will be EF angle del. So, what is the angle del here? Del will be tan inverse of imaginary part divided by the real part. Got it? So, now tan inverse IQ IA, sorry, this is IA not IQ, right? IA is 1, XQ is 0.8, V is also 1. So, tan inverse 0.8, and tan inverse 0.8 is 36.66. Just see how easily you will calculate all those things, how easily you will be able to do those things. So, just write the KVL equation, okay. Then separate this part involving IA and RA plus JXQ. Whatever is the angle of EF, same will be the angle of EF double dash. So, take EF double dash and try to calculate the angle of it. Okay. In this question, resistance was neglected. In other question, you may get resistance, then you have to expand this part, and then you have to take the imaginary and real part the way we have done here. Okay. So, you can practice for other power factor as well, that what will be the formula, correct. So, in this way you can calculate del here. 36.6 I am getting, you are getting 38.65. Tan inverse 0.8 is how much? Anybody else who is getting a different answer? Tan inverse 0.8 is how much? 36.6 or 38.65? $36.6 or 38.85. Okay. By the way, for any other power factor, this is for unity power factor and neglecting RA. For any other power factor, if you want to calculate del, it will be tan inverse, okay, IA RA sin phi, sorry, IA XQ sin phi, IA XQ cos phi minus IA RA sin phi divided by V plus IA RA cos phi plus IA XQ sin phi. Right? Have I written the correct formula? It is 38.65. Okay, then my answer will be wrong. 38.65. Correct? So those who knows the formula, tell me, have I written a correct formula? If you want to calculate del for any other power factor, you can use this formula. Okay, this is for lagging power factor. Correct? This is for lagging power factor. Correct me if I am wrong. This is for lagging power factor and RA not neglected. Okay. Now, if suppose you could have applied the same condition here, RA is neglected, so this part will be out, okay, and cos phi is 1, right, sin phi will be 0. So, I think I will be getting the same answer. Got it? So, this is in general formula for lagging power factor. From that formula, RA you can neglect and you can apply power factor to be unity. Okay. If suppose leading power factor is given, cos phi is cos phi, sin phi will become negative. You can write there. If suppose instead of generator, if this would have been a motor, then you have to replace these plus with minus. Rest everything will remain same. Okay. For if suppose this is a motor, you have to write this plus to be minus. Rest everything will remain same in the formula, and as per the given power factor you can apply. Got it, guys? Whether this formula is correct? Okay, it is correct. So I hope that you got enough practice of how to apply KVL equation in alternator. Now let me do one question where you will get a practice of that how to apply KVL in motors. Okay, so next question that I have is related to motor, and this is going to be the last question as well. A 3-phase 50-watt salient pole synchronous motor has per phase direct axis reactance X of D. Okay, now X of D is 0.8 and X of Q is 0.6. Resistance is negligible. Very good. Thank you so much. It is drawing full load current at 0.8 power factor lagging. Cos phi is given 0.8 power factor lagging. Okay. When the terminal voltage is 1 per unit, the per phase induced voltage will be, you have to find EF, right? You have to find EF, right? So you need to practice that how to draw the synchronous motor phasor diagram. Okay, how to draw the synchronous motor phasor diagram. You need to practice that. First of all, guys, what I will do, what is the power factor given? It is given lagging here. So for lagging power factor, okay, for lagging power factor, we need to apply this condition V cos del, right? V cos del, this is equals to EF plus IQ RA plus ID XD, right? For lagging power factor, you have to apply this condition V cos del equals to EF plus IQ RA plus ID RD. Correct? Then can anybody tell me that for leading power factor, what is the formula? What is the formula for leading power factor? I think it is V sin del, sorry, V cos del plus ID XD. This is equals to EF minus, sorry, EF plus IQ RA. Okay, am I correct? Can anybody tell me, Bindu or Medha, whether I have written correct formula? I hope that I have written, right? For lagging power factor, you have to apply this. For leading power factor, you have to apply this formula. Got it? And for unity power factor, it will be V cos del equals to EF, right? V cos del equals to EF. Okay. So what you can see that for any power factor we need to calculate the value of del. Okay. We need to calculate the value of del. So why don't we calculate del first of all? So how to calculate del? That's very easy. If you want to calculate del, just now we have written the formula. So del will be tan inverse, okay, IA, just see we have written the formula, IA xq cos phi minus IA RA sin phi divided by V. Here it was positive for alternator, now we will write negative, V minus IA RA cos phi because it is motor into IA xq sin phi. So this is the formula of del, right? Just see how easily we have applied this formula. Okay. For motor here we have negative, for alternator here we have positive. Now in this formula apply the conditions. What is given? We have been given that the armature resistance is neglected. So neglect the RA part here. Neglect the RA part, and this formula is as it is for lagging power factor. If it is leading power factor, sign will be positive. Wherever sign we have, we will write positive. Okay. Neglect RA. So if you will neglect the RA part, then your formula will be this one. Correct? Your formula will be this one, because they have written full load, and I told you that under certain condition IA you can take 1 per unit. Okay. So now write tan inverse, right, IA is 1, xq is 0.6 and cos phi is 0.8 divided by V is 1, I is 1, xq is 0.6, sin phi will be 0.6. Okay, if cos phi is 0.8, sin phi will be 0.6. Then what value of del you will get? The value of del that I am getting is 36.86 degrees. 36.86 degrees. That will be the value of del. Okay. Now, after that have a look. If in motors we will take EF as base, in generators we will take V as base. Okay. So EF if I am taking base, okay, then V will be leading the EF. Okay, because in case of motor the del is negative, so EF lags the V. Okay, this is del. Now, so how much and what is IA? Let's suppose IA lags the VA. Okay, so IA is lagging VA. Okay, so this will be my phi. Then what will be the psi value? What will be the psi value? Psi is the angle, sorry, this is phi, up to here, this is phi. Now psi is the angle between EF and IA. Okay, so what will be psi? Psi will be phi minus del. Correct? Psi will be phi minus del. And if power factor is 0.8, then what will be phi? 36.86, right? So just see 36.86 minus del is also 36.86, so you will get psi value equal to 0, right? You will get psi value equals to 0. Got it? So you will get psi value equal to 0. This is how you will calculate psi. So Medha, you were saying na psi will be phi minus del. This is here in motor for lagging power factor. Got it? Now, so psi value we have calculated. Which formula we have to use? We have to use lagging power factor formula. So this is our formula. Okay. So our formula that we will be using is V cos del. This is equals to EF plus IQ RA plus ID xd. Okay, this will be 0 because armature resistance is neglected. Okay, and id is ia sin psi, so it will be 0. So this will become 0 because id is 0. So you are getting ef as v cos del, exactly what we have in case of lagging power factor, sorry, unity power factor. So cos 36.86, and what we will be getting is 0.8 per unit. That will be the answer. Correct, guys? So just see, related to cylindrical rotor motor, everything is written on this page. Everything is written on this page related to cylindrical rotor motor. This is the formula that you have to apply for lagging power factor. If power factor is leading, wherever sign is there, it will become positive. You will calculate del from here. Then EF will be taken as base and V will lead in case of motor. In case of generators, opposite things we have. V is the base and EF leads V in case of generator. Generator del is positive, motor del is negative. Then as per the power factor, draw the IA. It is lagging here, we have drawn like this. Psi will be del minus phi. Okay, if it was leading power factor, then I might be leading V. Okay, then phi will be here, so phi plus del will be sine. So we could have added those, right? So this is how you will get sine id, and then as per those condition you will apply formula, you will get your answer, right? So regarding motor, okay, regarding motor, wherever you are learning machines, whatever is being taught to you regarding motor, if you are from any platform regarding motor, whatever is the important thing we have written here. So we have practiced 4 questions of synchronous machine, and whatever is important for the gate calc paper, I have discussed everything. I have given you a hint related to everything. Okay, if you will practice these questions in formula, surely you will be able to solve gate questions, and they are going to give these questions, right? So this is the end of this gate score booster session. Okay, I hope that you people have enjoyed a lot. So I have discussed almost 24 fantastic questions, and through these questions I tried my level best that you revise all important concepts of machine. I hope that you really liked it, right? Now I am ready to give you the same experience. I am ready to give you the same experience is another core subject of electrical engineering, that is power electronics. So I am going to take a gate score booster session on power electronics tomorrow at the same time, 4 to 7. So I will be very happy to see you people again in this session, okay, and we are going to practice very good questions of power electronics. So today you have prepared machines, tomorrow you will be able to prepare power electronics, right? And to get a regular updates about what we are doing here, you have to join our Telegram channel. The link is given in the description box. Here you will get a regular feed about all important information related to gate and PSU exam. You will get daily quiz as well, right? And then again I would like to remind you that do not forget to join this discounted test series plus program of IMS Gate Academy, where you will get these many number of tests, and it is a time to give test. So appear in those tests, okay, by our test series program. You will also get GQB booklet. So this is a time where you should be practicing more and more number of PYQs and the test. So you are getting everything here in this program at a discounted rate, okay. And if you are really enjoy the learning, teaching and learning methodologies of IMS Gate Academy, I would recommend you to join our Gate 26 and 27 program, okay, where you will get 800 plus hours of live online classes, okay. You will get exceptional material like theory book, exercise book and gate question bank, okay. You will get 12 personalized sessions. So gate is a very long journey. How to strategize your preparation, we will discuss by meeting one-to-one personally, okay, where you can discuss all your doubts. So this is what I wanted to discuss with you people today. We will meet tomorrow from 4 to 7 p.m. and we will discuss some very important questions of power electronics. And again I would like to remind you about our test series program. Now we are offering it at a discounted rate. Do not forget to buy it. Okay. So thank you so much for attending this session. I hope you have really enjoyed it. We will meet tomorrow, same time 4 to 7 p.m. and we will discuss power electronics, right? And do not forget to share this session amongst your friends, okay, so that all of them can also enjoy the benefits that we are giving here. Okay. Thank you so much for attending this session.